Just appears.
Looks like it's
Okay, didn't work. Okay. Yeah, so my name is Narodytska. I'm a researcher at VMware Research, and today I'll talk about our, I would say, latest project. It's a result of the internship that Andrew Wu did with me this summer on the frameworks we called Lemur for integrating large language models and automated program verification. So we started this project because there were a lot of success stories of using large language models for program understanding, and you see tools online that use large language models for program synthesis, for code repair, and so on. So recently, this summer, there was a CML paper where the author asked the question whether large language models can reason about program invariance, and they answered positively in this paper. So this motivated us to look a little bit more and see whether we can use these advances to speed up program verification. So first, we spent a lot of time. Oh, it's very small. Okay, we spent a lot of time playing with ChatGPT just to understand where we are, what we can do. Like we didn't have a real experience before that. So if you look at this very small program, when you have X and Y variables, and we run this loop, infinite loop, where X is just assigned X plus Y, and Y is incremented by 4 on each iteration of the loop, and we want to check that X never equal to 30. And we ask a simple prompt from ChatGPT whether it can provide us a loop invariant. And actually it did, you see, so it's actually a loop invariant. So Y is divisible by 4, it's a loop invariant. And you see this divisible module operator doesn't appear in the original program. So I'm a little bit afraid to say the word understanding, but it did show some signs of, I guess, understanding the program. So we thought, okay, it's a good sign. So can we do more? Can we actually have this process automated and have some improvements over existing state-of-the-art tools? So in terms of related work, if we compare with existing learning-based invariant generator, so that work that uses learning to generate invariants, there was a work there. It was from New Rips a few years ago, but they had quite a few constraints. For example, they required that each program has 3 parts, number of assumptions, or statements, one loop which contains if-else statement with arithmetic operation, and only one assertion statement. So they did put a lot of restriction on structure of the program that we wanted to avoid. So this is the question that we ask: can we leverage LLMs code understanding ability that appears there is one there for automated program verification? We had a bunch of challenges. I think maybe if people in this room try to do it, you face similar ones. So how we do this prompt engineering? It's not obvious. Then the other important part that we can't treat what LLM gives us as a true, right? It gives us something. It's a candidate. We don't know it's a true or false. Like, so it doesn't hold. It might be too weak. So we can't just take it and use it. So we need to use a formal verification to check the results of LLMs and in the loop. So a few kind of simple findings that we found. First of all, we realized that ChatGPT can't count can't count lines in the program. So we had to introduce these markers in the program and tell explicitly, give us invariant at this location, because often it would give invariant and this correct invariant, but in the wrong location. So it's useless because our procedure is automated procedure, right? So we can't go and manually check, and it really improved results. We were getting invariants in the right positions, and they were useful invariants. Another point is that what it returns to us is often like a wrong invariant. Like if you run it multiple times, it will generate you different candidates. Some of them are correct, some of them are not. So we have to take it into account as well. So some of them will be just wrong. So another point is that sometimes it's not enough to get one invariant. We have to construct a chain of deduction, so a chain of invariants that we need to construct to be able to prove the property. And in this chain of invariants, we check that the next invariant that we obtain implies the previous one. This is how we get the chain of deduction. Okay, on the high level, so what's the idea? We do the separation of responsibilities. We use large language models to suggest proof goals, to strengthen proof goals. So we ask, like, can you strengthen it? And to repair proof goals if we know that it's wrong. And for program verifier side, we will check the implication, whether the new invariant that we obtain implies a property. We need to check that it's correct, and we can provide feedback. For now, it's in a very basic form, but we do provide a feedback if we know that invariant is incorrect. That was provided by large language model. So in terms of results, we propose this calculus that defines a set of rules how to integrate program verifier with large language models. So some thing to highlight here that here we have calls to O, which it's an oracle. It's a large language model, and we can ask different questions like repair or strengthen invariant. And we have set of rules that define termination. We proved that we are sound. So it means if we terminate, if it's success, that property is invariant. If we fail, that it's not an invariant. But our calculus doesn't guarantee the termination. So for that, we build an algorithm, we design an algorithm that no more than just a strategy, how to apply this rule. So this rule that I showed on the previous slide, and we do guarantee termination for that, but we might return unknown. So at some point, we just might return unknown. So I'll give an example how it works. So we have, let's say we have this simple program, we have x equals 0, we have a loop, and we on each iteration of the loop, we increment by 4, and we want to check this assertion. So you would be surprised, it's a small program, but if we take a state-of-the-art verification tools from the latest competition, it's a snippet of the problem, but this type of problems can't be solved sometimes. So this on top says we call the verifier and the result was unknown. So we say propose. So propose means we do call to the oracle. It's a call to large language model, and we ask to propose the invariant in the beginning of the loop. And let's say it proposes that x is divisible by 2. It's a true invariant, but if you run the verifier, it might still return unknown because it's not strong. Okay, I forgot one thing to say. So whenever we get something from a large language model like this invariant, we don't know whether it holds or not. But what we do is say, suppose it holds. That's why it's assume, not assert. Say, suppose it's called. Can we prove the invariant? Right, this is the first step we are doing. So suppose it's called. Can we prove the invariant? And answer can be still unknown from the verifier. So for that, what we do is say repair. We come back to large language model and say, what you give us is not strong enough to prove the property. So repair, and then it will hopefully strengthen for us. So we have the new candidate, we new assume. We say, suppose x is divisible by 4. Can we now prove the property? Can we prove this assert? And in this case, yes. So the verifier says, yes, we can prove, but you see, we don't know whether this holds, right? We assumed it. We assume that it holds, but we don't know whether it's true. So the next step would be we have a decide rule. So now we have a change of the goal. So now we have to prove that this assume holds. And if it's true, so if this one holds, then we prove the property. So it might go another way. It's alternative execution. So large language model might propose something which is just wrong. You see, it might propose that x divided by 4 modular gets 1. So it is wrong, but we don't know it. So, but as I said, we always never take it for granted. We say, assume this holds. If false holds, of course, it implies a property, right? So the verifier returns as true. And now we want to check whether this assumption is correct, and verifier returns false, it's wrong. So we can do multiple things. We can either ask ChatGPT to repair, ask ChatGPT to repair, or we can just backtrack and ask for a different proposal. Yes, so this is high level how the algorithms work. It's all automatic, so we don't have human here. We do all the annotation automatically, and the loop runs also automatically. So we did some, I would say, initial experimentation with this algorithm. It's written in Python. We use OpenAI GPT. Better results we were getting with GPT-4, using it through the API call. And we used two verifiers, which is Atomizer and ESBMC. This is the best tools for among non-portfolio solvers in the latest software verification competition. So we filtered benchmarks. We get 50 short C. It's all C code, so it's all C benchmarks. We got 50 short. Shorted means why partially short? It's easier to verify, and another, it's actually quite expensive to run OpenAI GPT service. So we have 50 short benchmarks from latest software verification competition that was not solved by either of these two solvers, even they were the best solvers. So it wasn't solved either by SBMC or Atomizer in 20 minutes. So it just resulted they were good solvers. And the last one is what we are trying to do, plugging a large language model in the loop to generate this invariance. And as a result, so as I said, none of these two solvers individually can solve any of these 50 benchmarks, but plugging large language models in invariant candidate generator did help, and we were able to solve 25 of them. So this is all what I wanted to tell you about this project and the results. With a lot of comments we get, whether we can go from somewhat small program to a larger program. It's quite, I would say it's quite challenging in many aspects of it, even like, feeding large code base into LLMs might be also a bit challenging, and we need invariance, so we need something that makes sense, right? But maybe some modular approach can be, this kind of results can be used in some, first you prepare your program in some modules, some shorter one, and then we still thought it's quite impressive that it works for these programs that can't be solved by best tools out there. And of course, this work is limited. At the end, we still call the verifier. So we can't go beyond what the current best tools are doing in the program verification. Okay, that's it. Thank you for listening.
Is there a question for Nina? Yeah.
So how would you compare that? So if you're doing a lot of iterations, like how do you sort of compare the possible performance of like running your own LLM locally compared to using API?
You mean how many iterations was, how many calls we need to do, or how expensive was it?
Yeah, so like how many calls, and like if there's many calls, does it make sense to run this locally, like run a weaker model locally?
We didn't. Well, it was already challenging to get results with the best model with GPT-4 from OpenAI. So if we had to run it locally, we'll have to use some publicly available one. We even see improvement from 3.5 turbo to 4. So I'm pretty well. We haven't tried it, but I would guess it will be even more challenging to get it to work with a somewhat less advanced model. And we didn't have that many calls. It's 20 calls. Oh, okay, now we have questions.
Question. Look like for repair. Do you just say, give me a stronger statement?
For repair, if we know that a verifier proves that it's false, we say you give us a wrong suggestion, repair it. But we don't give a counter example now. We just say repair it. We know that it's wrong.
So it knows automatically that divisible by 4 is stronger than divisible by 2?
So stronger is different. Stronger we say when we can't prove it, when we don't have a fail from the verifier, we say unknown, right? So when unknown, we just say, okay, let's ask it for the stronger one. But sometimes verification, like in this example, when it's obviously wrong, we can get it's false. Then we have 2 different prompts. We say if it's false, we say we know it's false. But if unknown, we just say strengthen it. But you see, every time you have to check what it returns.
So do you have any comments on
So
complex control structures, nested loops, if inside loops and all that? How does it handle?
So the best we could do, like we have like a sequential loops, like 4 loops. If you have there are multiple things that it can't deal, at least for now. For example, if you have array and you have elements of the array in the properties, then it's very challenging. So there are constraints. Oh, okay, I won't say constraints, just we couldn't figure out yet how to do it. But for more complex program will be harder.
Do you think fine-tune models on code alone, like Lemur?
Yeah, we can even use an OpenAI model now. It's somewhat cheaper to fine tune, and there are even from the verification competitions, there are a lot of data. You have programs and you have properties. It might help. I hope it will help because
right.
now we know fine tune. Okay, no,
Sorry.
done.